be promoted from lecturer to chair. Before I introduce our most honorable and distinguished speaker, I have one announcement. So I've heard that there is a long tradition at the Institute of Students of Summer Schools taking lecturers to karaoke one evening, so consider that. And now to the introduction. So Professor Dr. Andrew Jackura, I think, did his PhD at Indiana University, I think in 2019 or 2020, 2019. And then worked at Old Dominion University in Virginia and University of California, Berkeley in California. And now he's a professor at William and Mary, also in Virginia. And he'll teach us about the most exciting topic of scattering in a box.
Thank you. So let me remind you that after the lecture here, please sign in if you haven't, to keep track. So my name, to follow the tradition of the other three, my email in case you want to contact me about anything regarding either the school itself or nuclear fuel body physics. So what has been discussed so far, different aspects of what I like to think of are modern tools in the study of fuel body, hadron, and nuclear physics. Sebastian's been talking to us about scattering theory principles, which is a generic framework to discuss reactions non-perturbatively, but by itself, it's not predictive. You need some sort of input, either from experimental data or some theory input in order to make some quantitative predictions or understanding of nature. So it's a generic framework. It works really well. It tells us how to describe basic reactions and how particles and resonances are manifested mathematically. But we need more than just this. And Andre's been telling us about concepts from effective field theories, which in the study of strong interactions, we have what we think is the correct theory, quantum chromodynamics QCD. However, as many of you know, and hopefully we've been emphasizing, it's kind of a hard theory to do anything with, even though you throw a lot of hard work at it. But these effective field theories allow you to, instead of worrying about some fundamental degree of freedom, if you only care about some system like hadrons where the quark and gluon degrees of freedom aren't relevant, then you can construct an effective theory to perform some systematic expansion and say something systematic and quantitative. But it's only valid in a limited range where it has been defined, and discussing topics that we know are the correct way to describe, say, the hadrons or nuclei, which are poles of these scattering amplitudes from scattering theory. That's a non-perturbative statement, so even though there's some perturbation theory here of some hadronic physics, you still have some non-perturbative things that are out of your reach. So again, good tool, gives you some understanding about the local interactions and what's going on, and allows you to make some quantitative predictions, but it's got, like every tool, it's got its range where it's useful. Another big thing, as Andre pointed out, is in these systematic expansions, often you get many, many low energy constants you need to fit the data, so then the problem becomes, impractical if you try to go to high enough orders. Then we've had lectures by Amy on lattice QCD. So lattice QCD is a non-perturbative, systematically improvable method to compute low energy observables from QCD directly. It works very well, and the way we make use of it in practice is to do numerical approximations via the correlation functions that Amy was talking about before, with Monte Carlo methods, stochastic methods, to estimate these large number of integrals. So it's a completely non-perturbative way to access low energy QCD dynamics, but it's defined only for Euclidean, for the most part of what's been pushed, Euclidean field theory, in which case you don't have access to real-time dynamics, so you cannot get access to reactions directly. You can get at static quantities like energy levels, so the kind of intro quantum problem, you put a particle in a box or two particles in a box and you get some energy levels out. The same idea here is that's one thing that we can get access to relatively easily. You can also get matrix elements between different energy eigenstates of your QCD system in the box. Moreover, you have that your system is defined in a finite volume. So even if you were to think about, well, maybe I can get some sort of scattering notion from this, this confined problem in a box disallows any notion of infinite volume physics, which is where we think about reactions. And again, reactions is how we think about few body physics. All of the hadrons and nuclei we see are consequences of scattering dynamics. So seemingly, you can get a lot of information from here, but we're missing some of the other tenets that these other two can get. The goal of my lecture is to introduce yet another tool based on finite volume physics, which is where we're going to look at generic principles of quantum field theories in a box to relate the lattice QCD and see what we can do to relate them to concepts from scattering theory or even effective field theory if that's what you want to do. So if you've heard of what the so-called Lucier formula or Lucier quantization condition, which has been pretty big in recent years as a non-perturbative method that links up scattering phenomena to lattice QCD observables, this is what I'm going to try to derive throughout these lectures. So that is my goal, and we will see, because like the other speakers, I prepared a lot more than what I could probably get through, but I will try my best. So, kind of to illustrate what I want to do, our goal is to link scattering amplitudes to observables from lattice QCD. And what I am really thinking about is energy levels. So I know Amy will discuss tomorrow about calculating some of these things from lattice QCD. I'll say something in a little bit as well. And again, to illustrate a picture, because I like pictures when I can. We can calculate, if we put, say, two particles in a box and we construct these particles, some hadronic particle of interest, construct them with these quark field operators that Amy was discussing, and calculate some correlation function. We can get some energy levels out. And what I want to do is link it to scattering processes. So this is some generic scattering amplitude. And if I think about what we see in experimental data as a function of energy, we see some bump for something very simple. And Sebastian's been telling us, well, that's how I link that to a resonance pole in the complex energy plane. So this seems difficult. I have something in the finite volume, the box, give it some length L, and I have something in the infinite volume. How are we going to do this? By the way, if you can't read my writing, because I can get sloppy when I get excited on talking about subjects, just scream at me and I'll explain what I'm writing. So the central object, which has already been discussed a few times in all quantum field theories, is the correlation function. So I'll write C of X, and I'll write a generic version of this. No, I didn't say anything about what space this is. Yeah, this is just a generic correlation function. Yeah, oh, well, I can throw time in there. that's not the interesting part here. So this thing measures the propagation, in kind of generic terms, of, I'll call it something, whatever that is. Could be a hadron, could be a collection of hadrons, from the origin to point X. This here creates that something at the origin, and this thing destroys it at some point X. So in general, these functions are very complicated. These operators are constructed from quantum fields in whatever quantum numbers you want to analyze. So if you're thinking about a pion, you just want to measure a pion propagator because you hope to get its mass or something. You construct operators that overlap to the pion, and then you can create pions, destroy pions, and measure their propagation. This also works for multi-hadron systems. Let's say you want to create 2 pions at the origin. You can construct 2 pion operators. They propagate and you destroy them at X, and then that, you hope, gives you some information about the scattering amplitude of 2 pions. So some notation, I will call CL a finite volume correlator. Correlation functions, I will call them correlators for short. And in this, and Amy will discuss them tomorrow, we can extract the finite volume spectrum of particles in a box. C, which sometimes I write as C infinity, depending on if I forget or not, is the infinite volume, so finite volume versus infinite volume, correlator. And this thing here, you can extract amplitudes via the LSZ reduction theorem. So in quantum field theory, usually a second semester version, or a second semester part of quantum field theory, you learn about LSZ and how to relate correlators or Green's functions to get at scattering amplitudes. So this means in the study of finite volume physics versus infinite volume physics, if I think about this as the central object, I want to think about how do I connect these two things. So the goal, to refine that goal, connect CL to C infinity. So for the remainder of this lecture, I'm going to develop some elementary notions and notations and things that we need, and look at the spectral properties of both of these, well, of primarily this correlator here, and try to remind you a little bit about this one, because a lot of it's already been said by Sebastian indirectly through the LSZ, but I don't have that much time, so I'll focus on this guy, and link it to what's the difference between this and this. And then, next time, we'll look at what if I'm creating a single particle, how does the connection look like, and then we'll look at 2 particles. Let me comment here, there's a lot of interest in extending these ideas beyond what I'm going to talk about. A lot of work has been going into the 3-body process, that's where a lot of my work has been, and looking at electroweak matrix elements of hadronic processes, so with correlators with some external electroweak current. So this is in the spirit of developing a rigorous framework to analyze few body dynamics using all of these tools in combination. So what I'm going to do in this connection, the idea, and here I'll say the finite volume correlator as a function of momenta. So you can imagine taking a Fourier transform, and I'll discuss details in a moment. What we're going to do is write the finite volume correlator as the infinite volume correlator plus some correction term that knows about the finite volume correlator, because it has to, and also knows about the infinite volume correlator. You can imagine I take this and I add 0 in the form of the infinite volume minus the infinite volume, and then I want to isolate this thing, because this is where scattering dynamics is. This is where lattice QCD can give me information. So I can link these two up, but I need to address what this correction term is. And if I can get at that correction term, that gives me the link between these two objects. So that's the goal. So I'm going to discuss some preliminary notions and look at the spectral decomposition. All right. So I'm going to work in 3+1 Minkowski space with a metric that's diagonal with mostly minus. You may ask, well, lattice QCD is done in Euclidean time. Why can't you do that? We can do that. It's easier to formulate scattering amplitudes in Minkowski time. And since we only changed the time signature, the energy of some correlator in the finite volume and the infinite volume is the same. All that's changing is the signature of the time. So if I think about energies, which is what I'm going to ultimately think about, the signature of space doesn't matter for this. So for the finite volume corrections, it plays an irrelevant role because the energy is a static quantity anyway. But you can always link that to the Euclidean time framework, which is what's actually used in lattice QCD calculations. But to make my life simple and not trying to think about Euclidean scattering, I'm working this. We're going to work in a cubic volume. You do not need to, but this is going to make life easier. With infinite temporal extent. So in the hypercubic lattice, I'm going to consider that the temporal distance is irrelevant. In practical calculations, that's true. We often do larger time extents than we do spatial extents. If you don't consider that, you need to think about Matsurbara frequencies. But even then, the effects are not as strong as coming from the spatial volume dependence. So, for first looking at this, ignore temporal effects. And I'm going to consider my finite volume to be subject to periodic boundary conditions. Again, you don't need to, but this is by far the most common and what I'm going to formulate everything in terms of. So this means xj is equal to xj plus L in whatever the jth direction is for j equals 1, 2, and 3. Yeah. Periodic boundary conditions. I was trying to save time writing, but I should have known better. I'll try to save it again. Cons for conditions. All right, so if we think about the spectrum of particles in a box, I'll draw my box again. Try to draw it 3D. I'm teaching classical mechanics right now. The most impactful thing I taught my students was how to do the dotted lines on chalkboards. I can't get them to care about rigid body rotations and Euler angles, but dotted lines they enjoy. I'll teach everyone now. So you hold the chalk kind of on the tip end, and you tilt it slightly downward or slightly towards the direction you want to skip it, and then it just skips. With the bigger chalk, it helps. If it's little nubs, it doesn't work. All right, so LLL. If I think about the spectrum, well, just like in quantum mechanics, if you have a confined system, the only allowed spectrum you're allowed is discrete energy levels, and we'll prove that in a little bit. So the Hamiltonian, acting on some basis states, which I'll call energy eigenstates, they're countable, so I have some n to count what they are, and they depend on the box size, right? So the energies are going to depend on how big the volume is. If the energy is bigger, the energy may lessen or grow, depending on what dynamics are at play. So I can think En is a function of L. By the way, I'll post my notes because I have a lot more words written than what I'm going to write. So if you fear you missed something, hopefully that will help. So in practical lattice calculations, what else do you have? You have lattice artifacts, or the fact that space-time is discrete. I'm going to ignore those. Those don't play a role in the finite volume physics I'm going to discuss. They're negligible in that sense. To start gearing towards how the correlator behaves in a finite volume, I'm going to start thinking about periodic boundary conditions on the operators so O of t and x will equal O of t and x plus L in whatever direction we're interested in. We're going to introduce the Fourier transform. So O t of x. And I'm going to Fourier transform in the spatial coordinates only. And if you're like me, I can never remember what the sign of the Fourier transforms are for 4 dimensions, 3 dimensions. Peskin and Schroeder's a quantum field theory book a lot of people like. One thing I really like about it is at the front it lists a bunch of conventions that are used in a lot of modern field theory books and papers. So it's a good reference whenever you're confused. And I have my Peskin and Schroeder's Introduction to Quantum Field Theory. We'll get there. I'm proving that, yeah. So we find my Fourier transform. I'm going to apply it to my periodic boundary conditions. And I'm using the usual conventions that were used in modern field theory books. P x. Some exponential. Now we have the shifted. I think that's right. So for the left-hand side to equal the right-hand side, since the momentum in the roll is, it's a redundant, I mean, it's a dummy variable in that sense. This extra exponential term on the right-hand side has to be equal 1. So you write it over here. So e to the I, p, L, or IL P dot E must be 1. For this to be true, this means that momentum has to be quantized, because as we go around the box, momentum can no longer be continuous, it must be quantized. So we have P equals 2 pi over L, N with N being some integer triplet. So you can kind of see LP must be periodic in 2 pi with some direction, and then I just move that over to get the P. If you had different boundary conditions, this won't necessarily be true. For example, if you're thinking about intro quantum mechanics, you usually think about fixed boundary conditions for some potential well, and the momentum quantization is different there. So this is our first interesting fact. Momentum is quantized in a finite volume. So this means the Fourier transform pairs that we're actually interested, what I wrote was a continuous integral. It's actually FT pairs. And I'm going to write this in one dimension. You can make it multivariate. Well, sorry. These are the L. Assuming an origin at 0 for x. So the Fourier transforms look like this, where the spatial components or the spatial degrees of freedom are integrated, because again, I'm not considering the fact that in real calculations you lattices in space. So it's continuous in x, but discrete in momentum. No, because the relationship, if I think about this, dp to 2 pi, if I think about some delta p over 2 pi, well, this thing is sum of delta n 2 pi over L divided by 2 pi, so 1 over L sum delta n. Okay. So one of the things we need to rectify in going between finite volume and infinite volume physics is the fact that momentum is quantized. So if you think about some correlator and you write it in terms of a Feynman diagram expansion, your loops won't be integrals. There'll be an integral in the temporal component, but there'll be sums in the spatial component. Let me write that a little. So when you're relating these things, because again, I'm really thinking about finite volume field theory, so it's a lot of the same techniques that you've already learned if you've taken field theory. You just need to make some transitions. Oh, sorry. P. And then delta functions will become L delta P prime P. So Dirac delta functions will become Kronecker delta functions. One of the key concepts that is used from Fourier theory in this relationship between discrete and continuous variables is the Poisson summation formula, which sometimes I see as the Poisson resummation formula. and I'm going to write it in a form that is useful for what we're going to do here. If you go on Wikipedia, you'll see some weird rule for this. But if you do some simple manipulations, i.e. take some sums or some integrals, I forget which way, you'll arrive at the condition I'm going to write. And that condition, I'm going to do this in three-dimensional space. So I have some finite volume sum over some function f. And I can rewrite this thing as a sum over some vector n. I'm going to run out of room. I don't like that. Let me make some space. 2 pi delta p prime minus p. Oh. So again, some finite volume sum of some function. It's equal to the sum over some new integer triplet n times the integral over the momentum. So now it's assuming p is continuous. E to the I L n dot p f of p. So I won't prove this formula. But essentially it says a finite volume sum can be written as a new sum over an integral over the continuous variable p with some phase over the same function. And depending on the properties of this function, we're going to see some key relationships between finite volume quantities and infinite volume quantities. As you see, you already get the smell of that here. So again, I will use this. I do not have time to go into details of Fourier theory to motivate that more. Yeah. Yes. Yeah, so p is discrete on the left-hand side. P is continuous on the right-hand side, but now n is a discrete variable. So I haven't said much details about this function, but there's some assumptions on its support in the argument space, i.e. There's no high degree of singular structure to it in order to cause any breakdown of the formula. You have a comment? I could write f tilde. It's still f tilde. Yeah. Is f. Yeah. That's kind of the background of it that I'm not discussing. That I leave it as an exercise to the student. For a single n, this integral is a number that depends on the n, yeah, for a fixed n. No. You could, but that is not going to buy you much, I think, because that's just that you're going to undo what I did to get here, which is from the original Fourier version of this, right? I'm writing it in this form explicitly. Yeah. There's an identity there that I've put it in this form on purpose. And the reason why, because I'll write it now. I'm going to drop the tilde because it's going to get annoying writing every time. So if I take the first term of that sum out, all right, so the first term will be a triplet of zeros. I can write something like this. So now if I think about some Feynman diagram where I have some integrals over momentum, or in the infinite volume theory, or some sums of momentum in the finite volume theory, they're generally going to be of this form, right? I have some integrand or some summand, infinite volume physics, finite volume physics. This is giving me information about the correction, right? So that's why I wrote it in that form. I will define a shorthand for the sum integral is this operator, because I'm going to end up writing this a bunch of times, and that's going to get annoying. So I'm taking this minus this term and defining this funky symbol in order to keep that. So then this will be equal to just this term here, the correction term. Now, what I'll show maybe at the end of this is that, and we'll see this when we discuss single particle physics, is that if this function is smooth, you can manipulate these integrals to show that the corrections scale exponentially suppressed in the volume. So if you have a large enough volume, the corrections are exponentially damped. If this function is singular, so there's some pole or something that is going on mass shell from a quantum field theory point of view, then that would, the pole form of this means that this function is singular. I can no longer use the arguments I'll show you for when the function is smooth to show it's exponential. So you need the infinite sum of terms, but that infinite sum of terms is again just this term right here, so the functions scale as a power law in the volume, all right? So there's kind of two types of corrections we're going to be interested in. One, which scale exponentially suppressed in the volume, and those that scale like the inverse power of the volume. These are going to be more dominant than the exponentially suppressed ones, assuming the box size is large enough that you can ignore them, but I'll go to those details later. All right, so that's some elementary notions. Questions or concerns at this point? Okay, so in the remaining time, I want to look at the properties of the finite volume correlator. Because I now have a mathematical way to link up sums to integrals. The finite volume correlator has different analytic properties than the infinite volume correlator. And I want to identify what they are so that we may try to form a correction. So let's go through the spectral decomposition. So again, finite volume object, I'll write it a little more shorthand. suppress the vacuum states. I'm going to assume for all of this that my operators are scalar objects, so you can think about it as creating like a pion. I won't even think about internal symmetries like isospin or anything. I'm just going to keep it as the simplest theory we can. An example to think about that I'll revisit is phi-4 theory. So the Fourier transform, this is where I'm going to kind of stop dropping the twiddles, is equal. So I write the 4-dimensional integral in x, but the L only applies to the 3-dimensional part. It's over all the time. Here, P is the 4 momentum P, which is the total energy in the temporal component, and the spatial component is the 3 momentum. And it's the total momentum of this correlator as it propagates from the origin to x. So plug that in there. Concerning the time ordering, so the time ordering of OX, O dagger O, is going to be OX, O at 0, Heaviside theta function enforcing that t is greater than 0. And then you have a term where t is less than 0 for the other time ordering. So we're going to substitute that into our correlator. And simplify it down. So our momentum space correlator is integral from 0 to infinity dt, integral L over the volume, e to the I p dot x, O x, O dagger, 0, plus the negative time component. I'm going to focus on this one. I'll let you do this one as an exercise and just state the answer at the end. It's the same manipulations. I don't want to do it twice. So now I'm going to insert a complete set of states in this matrix, in this vacuum matrix element, this vacuum expectation value. The complete set of states will involve the spectrum of our system, which we said at the beginning are these finite volume states. Let me be a little more, since I'm doing this explicitly, let me be a little bit more clear. Before I had an index n just to count them, really I need to think about a particular momentum configuration for each energy eigenstate. Or each energy eigenstate has a particular momentum configuration. So I'll write this. Where again, our Hamiltonian, which in principle is the QCD Hamiltonian in the box. No, not anymore. I'll make the p dependence explicitly because I'm working with the p variable. N, in the simplest case, is just counting how many energy levels I have in a more generic sense. You can also think it's also holding other quantum numbers that I'm just not writing explicitly. Yeah, it's not free. So we find CL of P. I end at 45. Oh my goodness. To quote Sebastian. Sum of N, sum of P, some integrals. Sorry, this sum is over P prime, because I have two P's here I want to distinguish. So the sum over P prime is in principle different than the P hiding in here at the moment. Okay. So I'm doing essentially the same steps when you, in field theory, if and or when you take it, when you derive the spectral representation for the propagator, which is the Shalin-Lehmann spectral representation. So now, under space-time translations, O of x is e to the I, the operator of P, dotted into x, O at 0. So I'm shifting this operator to the origin. Why? Now, P is h, and the momentum operator. So I know when this thing is now going to act on the right, it's going to pick up the discrete spectrum and the momentum of that state. Just like in infinite volume, there's always some ambiguity when you think about large time extent, when you want to start thinking about contour deformations, when you're thinking in the complex energy planes. To ensure the correct convergence, I'm going to do the same thing that is done in field theory and leave you to a field theory book to discuss some of the reasons why. But I'm going to replace my Hamiltonian with the Hamiltonian minus I epsilon to ensure convergence. And this is that same I epsilon that appears in all the Feynman propagators that you take to 0 to ensure it's on one side of the axis or the other. And then the epsilon goes to 0 plus limit will be implicit. So by doing this, now e to the minus I p dot x acting on en, l, and p prime will be equal to e minus I en minus I epsilon, again, the convergence criterion, e to the I p prime dot x. The change in sign is because I'm doing Minkowski time, remember. En p prime l. So this I'm going to substitute into here and do some manipulations. I will skip just a step or two and just write what it is after you do all that and leave you to work it out to verify. So CL of P, sum of n, sum of p prime. We have the temporal bit. Oh, sorry. This is E minus En plus I epsilon time times the spatial integral I'll define this function in a second. So with Zn of P and L is the operator, so not daggered, En P prime L. So finally, I'm going to do the spatial integral is an integral over x. X is only part of here now. This is exactly one of the rules I wrote down for relating Fourier transforms to delta functions. So this term here is simply L cubed times delta in P and P prime. So it enforces this P prime dummy variable to be P, the total momentum of the correlator. I can also perform the time integral. I will let you do that as an exercise for home. Hopefully it's not too bad. You know how to integrate exponentials. It's going to bring down the argument inside the exponential. And as t goes to infinity, you're going to be remaining with a pole. So finally, CL of P is L cubed times the sum over all the energy eigenstates plus the time reversed one. So our spectral decomposition of the correlator in the complex energy plane, and let me think about the E star squared plane. Why? Because that's going to be related to the S variable that Sebastian's been talking about, the S Mandelstam variable. And E star squared is just E squared minus P squared. So I'm getting rid of the momentum dependence in effect. By the way, when you do, and I'll leave this as an exercise, when you do this bit, you can combine the poles that come from there to where, so as a preview, the poles are going to look like sum over n, 1 over E squared minus En squared plus I epsilon. It's another reason why I'm thinking about the E squared plane. Anyway, so this is just a sequence of poles. Right, so E0, E1, so on and so forth, starred, squared, blah, blah, blah. So it's poles in the E in the center momentum frame energy squared plane. It's also poles in just the energy plane itself, if you just think of them in terms of energy. I'm making life more complicated solely for the fact that we want to link up the analytic structure of this to what's in the infinite volume. In the last couple of minutes, let me just write that down. So in the infinite volume, I won't prove it. And if you've taken field theory or field theory 2 whenever it's taught, you would have proven it. And if you haven't, you should just go through the exercise. It's very similar to what I showed. Whenever I erase the board in front of a crowd, I think about my vector calculus professor. When he started erasing, he would start doing this. I think for balance, I'm not sure. But whenever I erase the board, I always think about him. Yeah, we were always afraid he would just leave. So I'll write recall, but it may be for the first time. C infinity of P is going to look like the sum of j equals 0 to n zj over p squared minus mj. These are potential bound states that exist in your spectral decomposition. If you think about this as for an electron, as you normally do in field theory, you just have one, which is just the electron pole. But in general, I'm thinking more general. But then you can have discrete poles. But then you can have a continuous spectrum, which I'll write in terms of some sigma variable, which starts at some threshold when you have multi-particle production, a function which we just call the spectral representation, which again is written in terms of matrix elements of the vacuum and whatever operator to the continuous state at hand. I won't write it down. And then you have p squared minus sigma plus I epsilon. And in the complex p squared plane, which is the same thing as the E star squared plane, you will have poles, m0, m1 squared, blah, blah, blah. And then starting at sigma threshold, you're going to get branch cuts. Same analytic structure that Sebastian was discussing, and tomorrow you may finally get to unitarity after saying it for 3 lectures to describe the behavior of the functions around this cut. But the cuts associated with multi-particle production, and the key difference you see here in the analytic structure of these guys versus these guys is that you do have poles that you can potentially match up, and indeed we'll see for single particle states that this pole may be related to that pole exponentially close, as I was saying before. But when you start reaching to states where you have scattering continuum, then you need to really link the analytic structure of a finite volume correlator to an infinite volume correlator, and that's where this correction term will come in. So this is the motivation, and this is the kind of analytic structure reason of why we're doing it. Next time, we'll go through a single particle example using an effective field theory or quantum field theory as a catalyst to show how it works, and then we'll do for 2 particle states. Yeah, so one way to think about it is if you take the infinite volume limit, that the poles that would appear after wherever the scattering threshold is, they would start collapsing down into a single, to a line that is branch cut. The actual as far as I understand, the actual mathematical transformation from a sequence of poles to which are countably infinite to uncountably infinite branch cut is tricky, but mentally it's good to think that way. Okay. Yeah. No. Yeah. So using causality, which Sebastian's been talking about, you can argue with combination of causality and unitarity that on the physical sheet you're allowed poles on the real axis, a branch point corresponding to multi-particle production, left-hand cuts, which I'm not going to talk about, on the physical sheet. On the unphysical sheet, you can then have poles in the complex plane, which are forbidden on the physical sheet by causality, and those are associated with resonances. You cannot have a pole on top of the branch cut here. It invalidates unitarity. Okay.
Okay, let's thank Andrew. And do we have questions or comments?
Move out of the way.
I can start. I have 2 comments. Maybe it would be good to tell the students